Question 21. Why are energy levels negative? Well, electrons need to gain energy to leave an atom. If they have zero energy at infinity, then as they come closer they must have a negative value. So the electrons, and you must put this word, energy. Same thing. Part 2. The electron makes a jump from level C to A. Calculate the energy. Well, that's fairly simple. 3.4, take away 0.85. Yeah, energy gained is 2.55. That's already in electron volts. So there we go, 2.55 electron volts. Calculate the wavelength in nanometers of the photon absorbed by this electron. Well, firstly we need the energy in joules, so energy in joules is going to be 2.55 times 1.6 times 10 to the minus 19, gives us 4.08 times 10 to the minus 19. Then we're going to use E equals hc over lambda. We'll rearrange it. We want lambda is hc over E, so stick the numbers in. 6.63 times 10 to the minus 34 times 3 times 10 to the 8 over 4.08 times 10 to the minus 19. The wavelength we get is 4.9 times 10 to the minus 7. Well, to change it into nanometers, that's 490 times 10 to the minus 9, so 490 nanometers. Part B. Light from a distant galaxy goes through a diffraction grating, remember that. There's an alpha, hydrogen alpha. State how the emission line is produced. So how is an emission line produced? Well, electrons, again, move to a lower energy level. And if they do that, and therefore, lose energy or emit a photon. So, part 2. What adjustment could be made to the experimental arrangement that would make the emission lines more widely spaced? Well, that's just a narrower diffraction grating, so I guess you should reduce the grating separation if you want more lines per millimeter, same thing. In a lab, the wavelength is 565. Use figure 21.2 to determine the recession velocity. Well, we're going to have the change in velocity, change in wavelength, over the original wavelength is going to be the recession velocity over speed of light. So we need to find the change in wavelength. Well, the change in wavelength, if you read it from the graph here, okay, I guess is somewhere around 660, just over 661, something like that. I think it does it say anywhere. So if we use something like 661, take away the value in the lab, 656, that gives us a value of, I guess it'd be about 5, isn't it? Nanometers. So sticking the formulas in here, the numbers in the formula, we're going to get change in wavelength times c over lambda, 5 times 3 times 10 to the 8 over original wavelength, which was 656.3. I guess if we put 0.3 there, it's slightly less, isn't it? But that'll do. Now, do I need to put times 10 to the minus 9, times 10 to the minus 9? I could, but it will cancel out, so there's no need. If you stick the numbers in, the recession velocity comes out about 2.4 times 10 to the 6. So there it is, 2.4 times 10 to the 6. Part 4. Suggest why hydrogen lines play an important role in determining redshift. Well, it's very easy. It's just lots of hydrogen. It's the most abundant element. Okay, in the universe, if you like. So easy to see. Part. Light from a similar star systems that orbit around each other. So one will be going intense rather than bright. Okay, lower intensity. If the galaxy is further away, it is going to have a greater redshift. And finally, as a common orbit for two, so one is going to be going away, one is coming towards you. Okay, there's going to be if you like, a shift in, or period obviously being for the orbit, shift in the wavelength and in the redshift. Or if you like, you could have, if one's coming away, one's coming towards you, there's going to be a split, there's going to be a sort of double peak. So there's a split stroke, if you like, a double peak. Any of those will do.